finite element analysis. This is a numerical method which is used for solving problems of engineering and mathematical physics. It's useful with when you have complicated geometries, loadings, and material properties, where analytical solutions can't be obtained. As you know, there are two types of approaches to analysis of solving a problem, the numerical and the analytical. So the analytical solution or the exact solution, for example, if you're doing stress analysis for trusses, beams, and other simple structures, they are based on simplification and idealization. For instance, we can assume the mass is concentrated at the center of gravity and a beam is simplified as a line segment. And the design is based on the calculation or results of the idealized structure. And there are also factors of safety which are applied. In the finite element analysis, you find in real life design geometry is a lot more complex, may not be simplified like in a line element like a beam or a column. And the accuracy requirement in sometimes is a lot higher. Hence, we resort to finite element analysis. And brief history is that FEA grew out of the aerospace industry and post-war World War II, where there was need to analyze jets, missiles more accurately than in a simplified manner to get the stresses and deformations associated with those stresses. And this, of course, was paralleled by the growth in computers. The process itself, you start with the real world problem, you simplify or idealize this as a physical model, which can also be expressed in a mathematical form, and then we discretize that model or mesh it up. Discretization means to model the body by dividing it into an equivalent system of many smaller bodies or units, which are what are referred to as the finite elements. And these elements are interconnected at points common to two or more elements and the boundary lines of surfaces. We look at different types of finite elements, like one-dimensional line element, for example, a spring or a beam, and it's a line element like that line over there. And in the case of multi-story buildings, you consider each beam between column supports as a line element, and each column between floor levels is also a finite element. And in the 2D plane element, examples are membranes, plates, which we have already looked at, and shells, which we also look at. And the plane elements, 2D plane element, can be triangular, rectangular, or square. So you can have as that. You can also look at a 3D solid element, can be a 4-sided or 6-sided. This is an example of a 6-sided solid element. Then another important terminology we look at is shape functions, which are interpolation or bending functions, which are used to estimate the value of a required parameter between the nodes. In this case, the nodes are 2 points which join the boundary. And an example of a linear spring is a finite element. A linear elastic spring is a mechanical device capable of supporting axial loading, and the elongation of the spring is proportional to the applied load as shown. And as an elastic spring supports axial loads only, an element coordinate system, also known as local or natural coordinate system, can easily be selected as along x-axis, orientated along the length of the spring as shown below. So when you apply a load, for example, I have a spring between points 1 and 2 or nodes 1 and 2, and it has a stiffness K. and the forces applied to node 1, I have a force F1 and a force F2 at the two nodes respectively, and the associated displacements are U1 and U2. And if I was to do the force displacement, then it's linear as shown, and I can easily get my stiffness in that way. So the spring deformation is given by a displacement deformation delta is equal to the displacement at node 2 minus displacement at node 1. So I can write the deformation delta is equal to U2 minus U1, where U2 is that deformation and U1 is that deformation. And therefore I can also write the resultant axial force in the spring F will then be equal to K, which is the stiffness, times delta. And we have already seen the delta is equal to U2 minus U1. So I can say F is equal to K U2 minus U1. And that is, of course, at for two nodes, between two nodes, node 2 and node 1. For equivalent, for equilibrium of the system, of the spring, this system, that system which has two nodes at two points, node 1 and 2. Then, of course, for equilibrium, the force, the axial force F1 plus F2 must be equal to 0, or F1 must be equal to minus F2. So we can write that in terms of applied node forces. F1 is equal to minus K U2 minus U1, and F2 is equal to K into U2 minus U1. We can write these two equations in matrix form as shown there, where we have a matrix with K's, a matrix with displacements, and a force vector there. Or we can simplify that as KE UF as a matrix equation written as shown, where KE is the matrix of stiffnesses K. So this is the stiffness for one spring element, and KE is defined as the element stiffness matrix in the element coordinate system, or the local system. So we have a local system, and U is the column matrix of the nodal displacements, and F is the column matrix of the element nodal forces. So if you have a system of two springs, similarly, we can develop the stiffness matrix by introducing the nodes 1, 2, and 3. These are the two springs. The springs are 1, 2, and associated with each of the nodes 1, 2, and 3, we have a force and a displacement. So we have force F1, U1, F2, U2, F3, U3. And note F1, F2, and F3 are external applied forces. And these external applied forces, of course, then will be associated with an internal forces. So the free body diagrams illustrated below, where we just split and get the nodes for three springs. For spring 1, we have node 1 and 2, and the associated external forces and displacements as shown. And also we have for spring 2 as shown. So if we look at each of these nodes, for example, node 1, again will be associated with an external force F1 and an internal force or stress F1, small F1. And similarly, we have for node 2, there will be an external force F2, but associated with it, you have the effects of small F1 and F2. So you have an additional force acting on that node 2. For node 3, we have an external force F3, and also internal forces. So we can write equations for each of these springs in matrix form as shown below. So we can write an expression for node 1 as shown in equation 1, where the superscript refers to the element. And the element here is the spring. So the superscript 1 is denotes spring 1. Similarly, we can write an equation 2, which relates the stiffness of element 2 with the displacement 2 and the forces 2. And we can begin assembling equilibrium equations for the global matrix, where the global matrix represents the individual springs. So the global matrix then describes the behavior of the two springs. The displacement compatibility conditions which relate element displacement to system displacements are written as shown there. That is the displacements in node 1 will be the displacements and also displacement in 2. So there is a comma there like that, and we can be able to write these equations as shown, and also assembling or writing the matrix equations as equation 3 and equation 4. We can expand the equation 3, because remember equation 3 will also involve other nodes in the global system. So we can expand equation 3 by introducing an x row as shown. So equation 3 becomes the 3 by 3 matrix as shown in equation 5. And similarly, from equation 4, we can expand it so that we can position our stiffness matrices accordingly. And we can do the summation of the matrix equation 5 and 6 so that we have this equation which describes the stiffnesses of the two springs as shown. So if you refer to the free body diagrams of the three nodes, again as shown there, you find the final global equation given as follows. Okay, the global stiffness matrix will be given as that, and it is also known as the system stiffness matrix. So in summary, we start by finite element matrices and then sum them up to get the global matrix. So the finite element analysis for multiple elements can be summarized as F is equal to the product of K times U, where F is the array of applied forces which are known. We already know the externally applied loads. K is the matrix of stiffnesses. Sorry. I'll call you. U is the area of displacement of one of each degree of freedom to be determined, and it can be solved by matrix inversion or Gaussian elimination process. So we look at the next step from there. This was just to remind you of what you've already gone through in your other course, and we shall look at that in our next lesson. Thank you. Second lesson will be on displacement interpolations using shape functions. We want to see how we go about using the finite elements approach. Let's see first what are shape functions. Shape functions are very important to understand before we are able to proceed. So they are of the form, the matrix form, matrix F is equal to L times D, where F is the displacement at any point. Okay, matrix X is displacement at any point. L is the shape function, and D is the nodal displacement. Okay, so we have introduced here, there is any point and nodal. In our first lesson, we were talking about node 1, 2, and 3, but between the two nodes, there are points. How are those points displacing also relative to the different nodes along the boundary? So L is the shape function that we are introducing, and L is a matrix of functions of nodal coordinates, which are referred to as the shape functions. Therefore, a shape function is the displacement at any point when the specific nodal displacement is units and all other displacements are zero. So let me repeat that again. Shape function is the displacement at any point when the specific nodal displacement is unit and all other displacements are zero. Okay, so the accuracy of finite element analysis depends on the assumed shape function. To illustrate, let's look at a bar element. For example, in a truss, you have truss elements which suffer axial forces. And you have two nodes, and as shown, node 1 and 2, and you have displacements in the local coordinate system. You have a displacement x, which is what we call u, and you also have a displacement y, which we call v, as shown. And again, if you have an element with nodes as shown there in that diagram, you have a displacement in the local coordinate x, which is given by u, and similarly displacement in direction y. So it's in a plane x, y. But just as shown here, it's in the local. You have x in the local. For a line element, you have the local dimension x as shown. So and one, displacement effects. For example, if I have an element like this, horizontal with nodes 1 and 2, as shown there, and I give a displacement of unit at that one end there, and everywhere else is zero. So you can visualize the displacement at any other point in between will be a function of that unit and zero. So if I assume a linear function, then I'm able to get the displacement at any point as a linear function or a fraction between 0 and 1 as shown. And if I give n1 and 2 a unit displacement as shown there, and 2, and then node 1 remains at 0, then in an assumed linear displacement, again, I'll be able to define every point, displacement of every point as a value m, as shown there. So let the displacement in x direction be given by a value ux. So from this assumed linear relationship, you'll be able to find ux can be defined by this vector 1 minus m is to m, of u1, u2. So that is m, that is distance x over L, that is a factor m. Then the distance, the remaining distance there is 1 minus m. So if you look at these two diagrams where I give end 1 a unit displacement, so I'll find my displacement at the distance m there, given as 1 minus m. And when I give a unit displacement at node 2, then the displacement will be given by m as a factor of the two displacements at 1 and 2. So this is the relationship for a bar element which has an axial force, as shown, a linear displacement, axial force. For example, another example is if you have a bar element in bending. In this case, the axial force effect is ignored, and the deflection will be equal to v. Okay, again, we have these are the coordinates, the local coordinate x, and we have a coordinate in the y direction. So if it is in bending, then the slope will be given by, if the deflection is v, the slope will be dv by dx, which is equal to, we'll give it a value theta x there. So the effect of deflection in y at end 1 below. So let us give a unit deflection there at end 1, okay? The deflection in direction y there, and if it is in bending, then you see it will no longer be linear because it will have rotated at end A. So the effect of unit rotation at end A, at end 1, sorry, will be given by that shape, okay? The effect of unit rotation will be given by that, and the effect of vertical deflection at end 2 again will be given by that shape. That's a vertical deflection at 2, and the effect of unit rotation at 2 will be given. So we have this for each of these displacements, that is vertical displacements at 2 and vertical and unit rotation at the same end. So we have these two shapes shown with respect to end 1 and 2. And for us to determine the value, you have to do a polynomial interpolation in between. So we need to know what is the displacement at every point due to, for example, a unit rotation at end 2, and what will be the, similarly, what will be the displacement at any point due to a unit of vertical displacement at the same point. So you can see this is a little more involving than the linear relationship which we had seen above in an axial displacement. So that's why we use to determine the matrix of the shape functions L. Remember, L was the shape functions. You have to use polynomial interpolation, and that is what we want to look at. So again, I will leave us at that so that we can have that in our third video. So I will leave us with that for now. We'll have our lesson 3 on how do we get our polynomial. In our lesson number 2, we had talked about shape function, and this is the function of displacement at any point for an element subjected to bending, if you give a unit vertical displacement, for example, at node 2, the rest of the shape of the element will be like that, because at node 1 it's 0. So we would want to know at every other point, because it's not linear, we need to know how to determine that, because it's very important. And as we give the vertical displacement, there must also be a component of deflection. So we give a unit displacement. So you also give a unit rotation at the same node. So you have values for the effects of the unit displacement and also effects of unit rotation. For example, if I look at where I have shown is distance m from one end, the effect will be the sum of that and that as shown. But then how do we know that magnitude? So that's where we have polynomial interpolation. If you look at the shape, we want to determine the L1, that is the shape function for a vertical displacement. So let's assume that we have a polynomial relationship of values that we wish to determine. So the value y will be given by a value a x cubed plus bx squared plus cx plus d. This is just a polynomial which approximates to the shape. And the values a, b, and c will then be determined from the knowledge of the following. We know that at x is equal to 0, if we are taking our 0 from there, from node 2, when x is equal to 0, y is equal to 1, okay? So if we apply that assumed expression, when x is equal to 0, we plug in 0 where x is. So we will immediately know the value of d equal to 1. And at x is equal to L, our displacement is 0. Therefore, now we again plug our values. We replace x with L and give it a value 0. So we are able to come up with an equation, AL squared plus BL is equal to 1 over L. We also know from the shape, that shape there, when x, dy by dx is equal to 0 at x equal to 0. That is at node 2. So what is dy by dx of this polynomial here? Dy by dx is given by a value there, 3ax squared plus bx plus c. So therefore, if dy by dx is equal to 0 at x equal to 0, then you get a value of c is equal to 0, that equation. And also, we know dy by dx is equal to 0 also at x equal to L because of this shape. You know the shape there is equal to 0. So when we plug in our values, where were we? We will find that equation there, okay? So we can also put our values there from the equations above. We also know that we can be able to get these values, these equations. So by simplifying, at x equal to 0, y equal to 0, and d equal to 0, and dy by dx is equal to 1, we can be able then to find our values of a, b, and c. And I will not go through all that. That's just mathematical manipulation. And we are able to get our values of L2 is equal to a certain value there in terms of distance Lm, okay? We know m is equal to x over L, and therefore we can get a value of L2. So have a look at that also, and we can similarly determine our value of L4 by substituting 1 minus m for m in the above equation, and hence we can get our value of L, our shape value of L4. So in summary, then we have our L, equation L can be written as a matrix equation given as that. And hence we can say the diffraction at any point will be given by V is equal to that values, that matrix values. These are the values of the matrix. They look very long, but if you go through them carefully, you'll find they are not too difficult to comprehend. And from these equations, we can write our matrix equation in terms of values of L's 1, 2, 3, and 4, and the vector v1, theta 1, v2, theta 2. And it's very important if you look at the boundary conditions which we were using at node 1 and 2, they are the ones which are helping us to get the boundary values. For example, at x is equal to L, y is equal to 0. And therefore, we can get our value of displacements. Okay, so again, I will leave you with that to look at and also read further. Then we shall discuss in our next lesson. Thank you.